Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc at the University of Helsinki over in Helsinki, Finland. And I'm a cosmologist, which means I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a scientist, I love being a cosmologist, and I really enjoy chatting to everybody about all of the cool things I get to work on. In fact, I think one of the coolest things about being a scientist is being able to chat to people about science and about the cool stuff that I work on. So for anyone who's new here, for anyone who doesn't know, and a reminder to all the regulars, this is an interactive stream. The idea here is that you all can ask me questions, you can ask me anything you want. This is an AMA, ask me anything. You can ask me about cosmology, about physics, about space, about academia, about myself, about my cats, about Finland. So ask me anything. There are some questions I might not answer, but take it away. Ask me whatever you want. If you haven't done so yet, please do like, subscribe, leave a comment, do all of the usual YouTube things. It really does help boost engagement. If you're a first-time viewer, welcome. If you're a regular, welcome back. It is great to see some of the regulars already coming in here. I see we have Guadav, we have David Dunn, and Brath. Great to see you all, David Howden, Scott's. Really nice to see all of the regulars coming in. And I'm already seeing the comments here that it's been a while. It's been a while since I've been online, and that is very, very true. It has been a while. I think it's been 7 weeks, almost 2 months since the last Cup of Cosmology. And there's been a variety of reasons. I know some of you have checked in. Thank you. I've also been taking kind of a social media hiatus. So I haven't been replying to messages. So for anyone who reached out on Mastodon, thank you. I appreciate it. I just was not replying to social media posts over the last couple of months either. But yes, nothing to be concerned about. I've been off mainly because I've been doing a lot of things, and I had plans like 7 or 6 weekends in a row. And then we had a heat wave in Finland, and I was just like, it's too hot to exist, and therefore it's too hot to do a live stream. It's still very, very hot. I'm realizing already that I'm going to overheat during the stream, but that's okay. So yes, it's been a while. Thank you everyone for coming back. I know when I take such a long break, sometimes people might forget that I'm here and might not tune in. So appreciate you all coming back after a 2 months gap. Hopefully the streams will go back to a regular every Sunday schedule for a while at least. For like 2 weeks, then I'm off again for a week, then should be back. But we should be back to regular streams. Hey, John, great to see you as well. So yeah, it's great to see all of you coming back. As said, this is an interactive stream. So you can ask me anything you want, and I will do my best to try to answer all your questions. And I just realized one thing I forgot that is always part of my pre-stream prep, which is to clean my glasses. Which is annoying because I have a backlight and then I see everything on my glasses, which is why it's usually part of the pre-stream process. But I guess I forgot to do that today. But that is a minor detail. Whew. Okay, so hello to everyone coming in. What temperature is a heat wave? So Finland is not accustomed to dealing with heat. So a heat wave is considered having an average of like 25 degrees and somewhere in the country where it's 30 degrees. This is Celsius. I do not know what this is in freedom units, but in Celsius, like above 25 is considered a heat wave in Finland. Now, the problem is houses in Finland are designed to trap the heat, which in winter is great because it's nice and cozy despite being -10, -20 outside. The problem is the houses are designed to trap the heat. So in summer, it becomes very hot inside. But right now, my apartment is still 27 degrees. Which is a lot. Cooling down my apartment is apparently difficult. So I've been trying for the last 3 weeks. We had 3 weeks consecutive of heat wave, 21 days of hot temperatures, broken all previous records in Finland. But I guess that's going to be the thing going forward because, climate change. We are entering a climate catastrophe and that's not going to change anytime soon. So I think that's way too hot. I realized I was about to burn my mouth. They're way too hot. Wait on the tea. So yes, heat is going to become a problem, not just with my tea mug, but in general moving forward. But at least it's now a very nice temperature outside. I just need the inside to cool down a bit. But yes, as many of you know, I am very much a winter person. I like being out in the cold and the dark and the damp. And when it gets a bit too hot here, I'm just not in the mood for being energetic on live streams, which is the reason I haven't done a live stream the last 2 weeks. The previous weeks I was busy. In the last 2 weeks, it's just hot. And yeah, I know, Beth, it's not as hot as in other countries. 25 to 30 degrees is definitely milder than Spanish summers, but the buildings here are not designed for these temperatures. You don't have aircon in any buildings here, for an example. Most buildings don't have aircon. There was a whole week during the heat wave where there was no aircon in my office either because they just switched it off for some reason. So even though it's not a lot compared to what other countries get to, it's a lot for a country that is not prepared for that kind of climate. In the same way as like we get 20 centimeters of snow and it's not a problem for us, and a lot of countries, a lot of cities would stop functioning with 20 centimeters of snow. It just depends what you're used to. And Finland is very much not designed for 21 consecutive days of plus 25 degrees. But enough complaining about the weather. Time to chat physics. If you have questions about physics, as always, this is an interactive stream. So I did not prepare a topic today, which means it's up to you all to decide where we go with things. I see there already is a question here from Guadav about Daisy. Some final comments from the weather perspective, or keep discussing the weather by all means. Comment from Scotia. I guess it's warm for Finland. Yes, it's very warm for Finland. Back in Barcelona, I was used to plus 30 degrees, but Finland is not designed for more than 25 degrees, especially not for 21 days consecutively. Okay, comment from John. Do you like iced tea? Sounds like the good weather for it. Yeah, no. I'm not a fan of iced tea. It's wrong. Tea should be hot. Tea should not. I will drink coffee with ice, an affogato with ice cream, or just coffee with ice is great. Iced tea, no. My tea needs to be hot. The problem with iced tea is most people put sugar in iced tea, and you should not be putting sugar in your tea, in my opinion. Do whatever you want to your tea. Just don't come to near my tea with that sugar. My tea is always no milk, no sugar, no ice. A freshly brewed cup of jasmine tea is what we're drinking today. Is it a bit too hot for tea? Potentially, but it's fine. It's fine. It is always. I am convinced that in winter, hot drinks help you warm up, and in summer, hot drinks help you cool down. And I will accept no scientific evidence to the contrary here. I am used to 2.73 degree Kelvin, indeed, maybe a bit too cold. And I just realized I have a new prop for the stream, and I left it out of reach. So at some point, I need to go get a new prop that I have specifically for the streams. But currently, I left it out of reach. It will definitely appear. Okay. So I've seen there's 2 questions about telescopes and dark matter and so on. But first, there is a question from Guadav. Did we already talk about the recent DESI results about dark energy? Sort of. So DESI is the Dark Energy Spectroscopic Instrument. It is a ground-based telescope that is trying to map galaxies, and with that, it is trying to understand dark matter. So just a quick recap. Let me just bring up my usual thing here, and then we can jump into DESI. Oh, that is not the slide I wanted. I went one too far. Here we go. So, yeah, sugar is Americans' favorite food. It's in everything. I know, and I hate it. The fact that there was sugar in bread when I was in the US is something that annoyed me every single day. You do not need sugar in most food. Make it actually tasty. You do not need sugar to make things. Yeah, anyway. The universe as we know it has 3 main components. Everything we see, everything we're accustomed to, everything from the cat about to walk on my keyboard, to the stars we see at night, to me, to my tea mug, all of that is normal matter. Do not drink the tea, it is very hot. This is not for you. So I just have to move my tea away from a cat who decided to stick his nose in my tea. I moved it away, do not chase it. Okay, yes. So everything from my slightly mischievous cat to the tea to the stars you see in the night sky, that is normal matter. Normal matter only accounts for 5% of the energy budget of the observable universe. There is another 26.2%, which is in the form of dark matter. Dark matter is this weird type of matter that does not interact electromagnetically, but does interact gravitationally. This means that dark matter is essentially invisible. We know that dark matter is there due to its gravitational presence, but we cannot see dark matter. Dark matter is completely invisible. And then we have 69%, which is the remaining 69%, which is in the form of dark energy. And dark energy is this weird type of energy that is driving the accelerated expansion of the universe. It's pushing everything away from everything else. And that is basically everything we know about dark energy. We think it's pretty much constant in time. We think it could behave in specific ways, but we really don't know what dark energy is. And of course, the question here is, how do we know all of these things? And I'm so glad you asked. The main place that we know these things from, I'm going to put up a map and then I'm going to go off screen for 2 seconds. But let me just leave you up with the CMB while I go get a prop. Okay, so the question is, how do we know how much matter, how much dark matter, how much dark energy there is in the universe? And the answer is the CMB, the cosmic microwave background radiation. This here is the, oh, I got a new prop, I got a CMB volleyball. Now you have to put up with me having an actual CMB prop. Ha ha ha, because I didn't have enough CMB things. Okay, so the CMB, cosmic microwave background radiation, this is the oldest light in the universe. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. And what we can see here, there's orange spots, there's blue spots, there's kind of a gradient here. The blue spots correspond to cold regions, the red spots correspond to hot regions. So what this is the first light in the universe. You can tell it's been a while since I've done a stream because this answer is not coming as fluidly as normal. So in the early universe, there were 3 main components. Well, dark matter was doing its own thing. And then there were 3 main components. There were protons, there were electrons, and there were photons, which are particles of light. At some point, all of these particles were bumping into each other because the universe was extremely hot. As the universe gradually cooled down, the protons and the electrons could combine together to form the first atoms, and the photons, the particles of light, broke away and started traveling freely throughout the universe. The way they broke away depended on their initial energy or their initial temperature. And these photons, these particles of light, have been traveling freely throughout the universe ever since, and they have gradually been redshifted, which means their wavelength has gradually moved to the red. Their wavelength has gradually stretched, and now they are in the microwave range of the electromagnetic spectrum. So this is background light coming from the early cosmos that we see in every direction, and it is in the microwave range. So we call it the cosmic microwave background radiation. And by looking at the cosmic microwave background radiation, this thing that I have on a volleyball now, we can figure out how much of the universe is in the form of dark matter, how much is in the form of dark energy, how old the universe is, all of these, the shape, the age of the universe, when the first stars turned on, all of this is stuff that we can learn about from the cosmic microwave background radiation. I know the question was about Dizzy. I will circle back to Dizzy. I needed an excuse to show off my CMB beach ball, which I'm very happy with. I acquired it recently. Do not ask me where it came from. This is this is an older version, so most of you are used to seeing this version on my streams, which is the Planck one. This one here is the W map. It is a much older one, but it's the one that NASA put on beach balls. So now I have this one. As to the question of why is there red on the equator, that is the galaxy. So the way to visualize this is we are basically at the center of this ball, and any direction you look at represents the night sky. So this is kind of the observable universe, and we live inside it. The red at the equator here is our galaxy, which is producing a lot of light. Usually what we do is we then put a mask, kind of a filter, to get rid of this galaxy. As you see in later maps, like this one here, the galaxy has been mapped out. You do not see this red band in the center. If you stare very closely across the center, you can almost see a slight distortion where the map was applied, or where the filter was applied to get rid of the galaxy. So the red here just means it's at a previous stage of processing and they haven't yet removed this galaxy from the center. But yes, I don't have the CMB, the Planck version on the beach ball, but I do have the WMAP one. So that is pretty cool. And it is also a very difficult prop to place somewhere. The place I would put it is on my laptop, but there is a cat on my laptop. Anyway, it's over there now. Okay, so I'm going to circle back to Daisy, but sticking with the CMB. How long until the CMB shifts to other wavelengths, for example, radio? You'd have to wait quite a long time for the CMB, the photons in the CMB, to gradually shift more and more and more. And we calculated at some point, or we sent a question to our cosmology students at some point, advanced cosmology, to calculate how long it would take the CMB to shift to a redshift where it's either no longer visible or, well, it's still not in the visible range, but where it's would be completely different to what we see now, and you'd have to wait quite a long time. So it's not going to happen anytime soon, but probably in about 100,000, 200,000 years, we would be closer to the radial range of the electromagnetic spectrum. I do not think I have a slide of WMAP, so I cannot show you what this would look like in this usual projection, because I normally just have the Planck one open. So I don't have the WMAP one for comparison, but now I have the WMAP ball instead. Okay, so CMB, cosmic microwave background radiation, allows us to figure out the components of the universe. Through the CMB, we get this very, very detailed pie chart where we know that 4.9% is in the form of normal matter, 26.2% is in the form of dark matter, and 68.9% is in the form of dark energy. Now, the thing about dark energy and dark matter is they're very, very difficult to study. Dark matter is invisible, very hard to study. Dark energy, I say, like, we know that it's causing accelerated expansion of the universe, but how do you study an energy that does not behave in the same way as the energies we're used to? Yeah, there's a comment here from Pratt that you expected millions, if not billions of years. I would have to recalculate that. I have in mind that it would be about 100, like order 10 to the 5, but it might be 10 to the 6. I would have to check that. So it might be order millions, but yes. Does that mean we would pick it up as interference on radios? Yes. If it shifts completely down to the radio spectrum, yes, you would pick that up in as a background noise. I mean, there is still this background radio noise everywhere in the galaxy anyway, but this would add to it. Okay. My cat is sat my cat is being a very good loaf on top of my laptop. Can I disrupt my whole setup just to show you the nice little loaf that I have here? Yes. That is Otto. Otto is being very cute. Otto has been demanding attention all day and is not happy that he is currently not the center of attention, which is why he sat on my laptop, because then I can still give him attention. He's a very sweet boy. Okay, so dark energy, this weird type of energy that is driving the accelerated expansion of the universe. Now, studying dark energy is very, very difficult. But what we can do is we can use the fact that dark energy is driving the accelerated expansion of the universe. So this means that dark energy is affecting how galaxies look or how structures look in the universe. So by taking a detailed map of galaxies, of course, we have the idea that the further we look into the universe, the further back in time we're looking, just because of how long it takes light from distant galaxies to reach us. So the further out in the universe we look, the further back in time we're looking. So if we can create a detailed 3D map of all of the galaxies, or at least galaxies close to us, we can then kind of get a snapshot of how structure in the universe has behaved at different cosmic time points, which means we get an idea of how cosmic structures are changing over the years, which gives us an idea of how dark energy is causing these cosmic structures to change. So this is the principle behind the Dark Energy Spectroscopic Instrument, DESI, which is a ground-based telescope that is trying to map all of the galaxies it can possibly reach. Now, already last year, we got this very, very, very amazing map from DESI, the Dark Energy Spectroscopic Instrument. Every dot here represents a galaxy looking further and further out into the universe, or further and further back in time. And at this point, they had already mapped 6 million galaxies. My voice is not used to doing these streams anymore. Need to get back into the habit. So every dot here represents a galaxy. These are the first 6 million galaxies that DESI mapped. This image was released in April last year. So together with this map, there was the study of how is dark energy behaving? What is dark energy doing? And there were some very interesting results that came out, kind of showing that dark energy seems to be thawing. So dark energy seems to be changing its behavior throughout cosmic evolution. So the way dark energy behaves today is slightly different to the way dark energy was behaving in the past. Now, this is a result that came out last year, and it was still kind of like, we need more information to cross-check this, to validate this. It's still early days, but this is what the data was hinting at. Now, Fast forward to this year, April this year, there was an update to this saying that they've done more checks, they've added more data, and these results are getting more robust. So the latest DESI results that came out in spring this year show that this is still the case. We are still getting this kind of thawing dark energy, this time evolving dark energy. It was kind of a validation that the DESI people think their results are now more significant than they were last year. So this is looking like the more and more likely answer, or the more and more likely result from DESI is that dark energy is time varying. Now, I know the question that was actually asked by Guilov is, have we already talked about this? And the answer is yes. Last year, when these first results came out, I did a whole stream about the first results from DESI. And back in spring this year, I did a stream with the title, I think it was something like Cosmology News or New Stuff in Cosmology, where I discussed the results of 3 different experiments that released results in spring this year, which included DESI, the Atacama Cosmology Telescope, and KIDS. So yes, in answer to your question, Guadav, yes, we have talked about DESI, but to summarize, DESI Dark Energy Spectroscopic Instrument is searching for, or is mapping galaxies to figure out how galaxies have changed over time, and therefore to figure out how dark energy is behaving throughout cosmic evolution. The first results from DESI, released last year, showed that dark energy is changing throughout cosmic evolution. It is not constant. The idea of dark energy being a cosmological constant seemed no longer as viable. And the new results that came out at the beginning of this year show that this is probably a robust result. So they added more data, they added a more detailed analysis of the data, and they are finding the same results. So it's very, very cool, and it's kind of showing us that maybe there's more to the dark energy picture that we haven't fully understood yet, which we know because we don't know much about dark energy. So, yeah, sticking with DESI, and then I'll answer the other questions. I see there were a lot of questions coming in early on as well that I want to get back to, because I went on a tangent to show you my new CMB prop. Again, don't ask me where I got it, but I have a new CMB prop. It's very cool. The reason I say don't ask me where I got it is because this is like a limited edition thing. There's only about 100 of them in existence. Of course, you can print your own, you can get a beach ball and put a pretty picture on it. But this is one of the NASA ones. Okay. Comment from John here, a question from John. Is the variable dark energy hinted at in DESI consistent with other cosmology surveys, or are DESI results in tension with other surveys? So DESI is the biggest survey of its kind so far. I'm just going to show you again this image here. This was 6 million galaxies mapped. Now, before this, we had something like the Sloan Digital Sky Survey, which is this one here, which had substantially fewer, less than 1 million galaxies mapped, and to not as far redshift. So what I mean by this is the results that we're getting from DESI are new, they're groundbreaking. It is the biggest survey we have so far doing this type of cosmology. So in that sense, it's quite hard to compare DESI to previous studies or previous analysis, because DESI is kind of a first of its kind to do this much information and this detailed map of galaxies. Now, there is a thing that in our standard model of cosmology, we consider dark energy to be constant. And this is what is supported by things like the CMB. So these new results might seem like they're in tension with our standard model of cosmology, but CMB maps like the one I have behind me, Planck, things like this, these all look at a very different scale or very different cosmology probes to what DESI is looking at. So even though it might seem like the DESI results are shifting away from our standard model of cosmology, which is supported by the CMB, this is not directly something that is constrainable or measurable within CMB physics. So while it might seem that the DESI results are new, they are interesting, they are definitely pulling us in an exciting direction for physics, but I wouldn't say they are in tension with existing results. They are more expanding our information about how dark energy behaves. Okay. Question from Prath here, and then I'll go to the other questions here. A question from Prath: how is redshift used as a unit of length? Excellent question, because I just flashed this Sloan Digital Sky Survey map, where you might have noticed that the diameter is measured in redshift. Now, the reason we do this, so redshift is an indication, can be used as an indication of both how far away and how fast an object is moving. So when talking in cosmology, we often use redshift as a kind of quantity of time. When we say like when the universe was at redshift, whatever. And here we're talking about basically the evolution of scales, the evolution of distances and sizes. Now, the reason we're more likely to use something like redshift rather than distance when looking at distances is that the redshift kind of accounts for the expansion of the universe. So distance is something that we're used to it being quite linear. You know, you go out a bit further, your distance increases linearly. When using redshift, it's not necessarily a linear increase because it factors in the fact that space is expanding. So we can use redshift to kind of give us an idea of what distance an object is. If I say something is at redshift 2, it means it's not within our galaxy, it's quite far away. And it also tells us how far back in time we're looking. So whereas you could say this galaxy is 5 megaparsecs away, for an example, it is much more informative from a cosmology perspective to say this galaxy is at redshift 0.1. Now, the thing is, they don't scale directly. You might be able to say, like, this distance is equal to 0.1 parsec or megaparsec. Sorry, this amount of megaparsec is equal to this amount of redshift, but these do not scale linearly because redshift grows much differently to the way the traditional distances do. So in cosmology, we use redshift both because it gives us a kind of historical time point of this is the time at which something happened in the universe, and it gives us a distance. Using the fact that we know the speed at which light travels through space, we can use redshift as a measure of distance. And just to give you an idea, when we look at the cosmic microwave background radiation, this thing here, we are at the center of our observable universe, so we are at the center of this sphere. So this sphere of the cosmic microwave background radiation is located at redshift 1100. And this is why it gets quite hard to think about it, because redshift 1100 was 13.3 billion years ago, whereas if we look at something at redshift 0.1, the light was produced, you know, a couple thousand, 100,000 years ago, maybe a million years ago. So it's kind of a shift in how we talk about things in the universe. It is very common in cosmology to describe objects being at a specific redshift because it allows us to conceptualize how long it's taken that light to travel towards us. A comment from Guadav here, think of redshift like Doppler shift. The higher the shift, the more distant an object. Yes, but also Doppler shift is linear, whereas redshift is not necessarily linear. Okay. Sticking with these questions, again, there's some questions that I want to go back to. There was just a comment from Guadav here. You are currently processing an astrophoto taken by amateur gear. Great. Astrophotography is amazing. Whatever your gear, it's very cool. In my new image, there are hundreds of galaxies. I'm blown away by how many galaxies we can capture in a single image with cheap gear. Yeah, it is amazing to consider just how many galaxies there are out there. And, you know, every galaxy has millions and millions, billions even of stars. It's just insane to think about the size of the universe sometimes. Like there's so much. This universe is so incredibly big. And we are just this tiny species on this tiny planet in one insignificant galaxy in a massive cosmic web, and that is both terrifying and extremely reassuring, in my opinion. Question from Guadav here. How do we know how much redshift equals how far an object is? Well, you can calculate the exact distance to an object via its redshift by using the relationship that we have between these. And this is actually something that also appears in the no, that's not a good way of explaining it. So when we look at galaxies moving away from us, we get an idea on their velocity, and then we can use their velocity calibrated with some distance to get an idea of the redshift. So the redshift can be used to calibrate how far away an object is by using either the velocity. So you need either the velocity or the distance at which it's traveling to get the redshift, but I'm rambling. We basically have this cosmic distance ladder, which allows us to figure out how far away an object is at a given redshift. And there's some that we just know by memory because we use them a lot. So, for an example, I know that the CMB is at redshift 1100. If you ask me how far away the CMB is in actual distance, I'd have to calculate it or give the number of 42 point something, about 43, no, not 43, about 48 billion light years, which is also not a useful concept to think about because light years is such an light years is also a confusing unit to think about. Comment from Varthia, astronomical distances should be measured in petameters or exameters instead of light years. Yeah, but then once you've got to the point of like it's 10 to the 15, at some point you need another name for things. And light years make sense somewhat. It's the distance that light can travel in a year. And megaparsec is the average distance between galaxies. So the kind of quantities that make sense in quotation marks. Yeah, at least we don't use CGS, which is one type of unit convention that is used in some fields that is extremely messy. And that is very much an inside joke. They're just throwing shade on astrophysics for using CGS units, which is centimeters, grams, and seconds instead of, meters, kilograms. Anyway, yes, if you've ever had to work with CGS units, you know why I'm complaining about CGS units. But that is very much a niche joke, so don't worry about that. Okay, now there were some other questions that I wanted to answer, but I think we've answered these current ones here. So we were talking about dark energy and the DESI experiments. There were also some important questions I should answer. When my cat walked past and sat on the laptop and I showed my cat, there was the question of how old are they? To tell the cat he's fabulous, he knows, he's wandered off to the window now. And cats do indeed need warmth. So my cats are about 9.5 years old and 7.5 years old. They've been with me for 9 months now, already 9 months. Oh no, 8 months. 8 months. They've been with me 8 months. They are very good cats. They are rescues. They are half brothers. The 9.5-year-old is called Otto. The 7.5-year-old is called Gutte. They are both very, very precious boys and very mischievous boys. And I made the mistake today because you might remember when I first got them, I was trying to figure out, do I feed the cats before the stream or after the stream? And I realized the best time is to feed the cats before the stream because otherwise they get impatient. I did not do that today because my whole schedule shifted. So the cats have not had dinner, and that is why they keep coming over for attention because they're expecting dinner. Question from Ben, will the DESI results affect distance redshift relationships? Not really, because if we think that dark energy is causing the expansion of space-time today, or the accelerated expansion of space-time, redshift already accounts for the expansion of space-time. So it won't change the distance redshift relationship, and it won't change the measurements we've already done for distances and redshifts. It will just change the way that the further out we go, the bigger effect this might have, but it won't change the relationship per se. It might just correct some of the ones we've already done, but it won't change the relationship of distance and redshift. It's coming from Scott. You've never heard them mention megaparsecs in Star Trek. It kind of blew my mind when I learned how long it was. Yeah, I think Star Trek might not be a good source for scientific accuracy. I mean, it's not the worst for scientific accuracy. At least they don't have little midi-chlorians living in our blood to control the force. But yeah, I'm not sure if Star Trek talks about megaparsec. Light years kind of make sense from our perspective, but it does very much assume the definition of a year, which is not absolute. But also when you're talking about megaparsecs, it assumes meters, which is, a quantity we've come up with that is not a universal quantity. In a sense, talking about how much light has traveled while we've done one rotation around our star, I feel like that concept is more transferable to other civilizations than this stick is a meter. This is our measurement device. This is not a meter. This is not to scale. This is about half a meter. But, if I say, this is my measurement scale, it's a meter, it's defined like this. It's much easier to define things according to things like, the time it took us to flip around our star once. How far did that light get? Yeah. Okay, the cats are years old, not months. I thought they were kittens when you got them. No, they were older cats when I got them. They are rescues. And yeah, they're 9.5, 7.5. They are not young ones, but they are very, very sweet. And they're really they're well settled and they're getting used to people. Okay, coming from David Howden here. So if we looked at the sky once it has shifted into the visual spectrum, what would it look like? I'm not sure what you mean. If you're talking about the CMB has gone past the visible spectrum. It's in the microwave range, which is a longer wavelength than the visible spectrum. So it's not going to go back to the visible spectrum. I'm guessing that was your question there, David Howden, that you're talking about the CMB. If not, please let me know what you meant there. Okay, now I'm going to go to the top of the comments and I'm going to read through all the questions because I know there were some questions I missed because I spent the first 35 minutes talking about Dizzy Well with a sidetrack to show you my new CMB prop, which I had to show off. Okay, so we got the question. I'm going from the top now, and then I'll catch up to the bottom. So we answered Dizzy. I complained about the heat. I complained considerably about the heat, yes. There was a question from David Howden. There was something in the media about a new telescope that will help detect dark energy. Suspect that's that's a sufficiently vague description to make it impossible to work out what I'm asking about. Might actually be the Vera Rubin telescope. Now Vera Rubin is doing more dark matter. It will also do dark energy. Okay, just had to use up my tea because it was at the point of getting cold. So in addition to DESI, the dark energy spectroscopic instrument, there's another few ongoing experiments trying to help us measure dark matter and dark energy. Now, of course, there's the Euclid telescope. Euclid launched 2 years ago now, and it is measuring. Yes, it launched 2 years ago. It is also trying to measure dark matter in the universe, and it will give us some insight into dark energy, but not so much. So there is part of the Euclid experiments that will be kind of a cross-check for what DAISY is doing in terms of dark energy, but it is not the main purpose. So Euclid really is trying to measure dark matter. Euclid is already up and running. We've already got some very pretty pictures and images coming out of Euclid. We've got some kind of side quests and astronomy results coming out, some astrophysics results coming out. We do not yet have any cosmology from Euclid, but stay tuned. Cosmology results from Euclid are expected early next year, or maybe spring next year. So Euclid will start giving us data next year. Now, as to the other one, I'm not sure if this is the one you were referring to, but Vera Rubin is an amazing observatory that used to be known as the Large Synoptic Survey Telescope, so some people still refer to it as the LSST. It is in Chile. It is also occasionally called the VRO. What did VRO stand for again? Yes, the Vera Rubin Observatory, of course, the VRO. So its purpose is to study dark matter and potentially dark energy as well. And Vera Rubin did actually have its first light in June this year. So the first light is basically the first time you turn on the telescope. When the first light hits the camera, that is what we call as first light. Now, once the first light has happened, then that allows us to do the final calibrations, and then you can actually start getting the scientific images not long after that. So Vera Rubin had its first light in June 2025. I'm not sure if this is the one you were referring to earlier, but there was also the comment from John of, have you seen anything neat from early results from Vera Rubin data? So I assume the question that David asked earlier on was also about Vera Rubin data because it's been in the news. So Vera Rubin Observatory is trying to map dark matter. There's a telescope that sits in Chile, has a very big mirror. It has a very big mirror, but also some very, very cool cameras. And it is trying to measure dark matter. We have had first light from Vera Rubin, but so Vera Rubin will, in a sense, be very complementary to what DESI is doing. We expect that there will be some overlap with their data, and it will be a good cross-check. But Yes, it will also create a survey of the night sky, and it will use that to study dark matter with some insights into dark energy as well. So there have been some kind of like first release images appearing, but the first light itself was technically in June, so the full data will start in. Let's just recap. Sorry, I realized I was rambling there. Vera Rubin Observatory, named after Vera Rubin, who's an astronomer who was extremely essential to our understanding of dark matter, or to giving us everything we know about dark matter today. We would not be where we are without the work done by Vera Rubin. So the Vera Rubin Observatory, named after Vera Rubin, is a telescope in Chile. It's been under construction for years. There were many delays, especially due to the pandemic. Vera Rubin took its first light in June this year. So we already have the very first kind of fancy picture just to show that, look, we built a telescope that works. We don't yet have any science results from the Vera Rubin data yet. We just have the very preliminary first light, I believe. Let me just check that there hasn't been any results already. I believe the only thing we have so far is first light, but let me just double check that just to be sure. Yes, for now it's mainly just the first light. Now we expect that it will start taking the more like cosmology data properly in the next few months, but we do already have the first light, and it is very cool. First light. I don't have any of the images loaded because they came out very recently and I haven't had time to load them up. But if you search for Vera Rubin Observatory first light, you'll find the cool images. So yes, just to recap, I'm guessing the question that David asked earlier was about Vera Rubin. It's very cool. It's going to help us understand dark matter, and it's going to shed some light on dark energy. It's had its first light in June. We expect cosmology data to start being taken soonish. All of the data will be made public after a 2-year embargo, but I expect we'll already start getting preliminary results next year from Vera Rubin Observatory, which is very, very cool. So, yes. Vera Rubin, very cool experiment, ground-based, going to help us understand dark matter and dark energy, will be in some regards complementary to both Euclid and DISY, but doing it in very different ways. So yes, David Alden, you think it might have been the Vera Rubin one that you asked me about earlier in the stream, and that John then asked me about later on in the stream as well. That would make sense because that is the one that people are currently talking about, especially because we just had first light. And I just forgot to put the images in. And if you all were wondering where I was pulling my facts from, this is I like being transparent about how I do things and how science works in general. I couldn't remember these facts about Vera Rubin Observatory. I just had the Wikipedia page open. So if you wonder where I was getting the name, just reminding myself of the name and when it had first light, I had the Wikipedia page open. In case you wonder, sometimes where all of my facts come, or if you see me reading, it's often the Wikipedia page. Because I'm not an infinite knowledge, I do not have an infinite database of random knowledge in my brain. I have quite a lot of random knowledge and random song lyrics, but sometimes you need to ask the internet for advice. And as long as you trust something, like, yes, get your facts from something like Wikipedia before Google AI or whatever AI summary. Yes, I would trust Wikipedia above all of those. Question from John. Okay, let me just check before we switch to Atacama if there was anything else here about, yes, Vera Rubin Observatory is also identifying new asteroids at a very fast pace already. Yeah, I guess Vera Rubin Observatory can already do asteroids. Yeah, that makes sense because it's a pretty big telescope. Yeah, cool. I forgot that that's something that Vera Rubin is doing as well. Maybe we should do a whole stream about Vera Rubin Observatory now that there has been first light. I will think about that. I don't yet have a plan for next week's stream. Maybe we do a special about Vera Rubin because then I can also talk about Vera Rubin, the person, and why the telescope is named after her. Because you all have heard me say many times, probably, that I do not think telescopes should be named after individual people. This is a stance that I still stand behind. I do not think telescopes should be named after individual people. But if you're going to name your telescope after somebody, Vera Rubin deserves a telescope named after her. So, not saying we should name telescopes after people, but if you're going to, Vera Rubin's a good one. It's a very big and very fast telescope. Yes, I'm surprised they didn't call it the Big Fast Telescope, to be honest, because that's usually how we name things. Maybe next week we do a whole stream about Vera Rubin and the Vera Rubin Observatory, and then I get to show you the nice images. Let me make a note of that, because otherwise I will forget. I'm just putting next week. I should add a date stamp to this. Today is, yes, next week, Vera Rubin. I get to talk about dark matter, yes. Then I can talk about Vera Rubin, the person, and Vera Rubin, the telescope. So, digression here. I like digressions. When don't I digress? And then Atacama Cosmology Telescope question, and then I go back to the top, because I've basically answered the first 2 questions in the stream so far, and a lot of follow-ons. So, when writing a PhD thesis, there are some things that people are strict about. You know, it has to be a formal scientific document, but there's always a bit of wiggle room to add your own personal stamp on your thesis, which, you know, some people do in different ways. Some people draw their own pictures. I had very snarky footnotes, or I have very snarky footnotes in my PhD thesis. It's not, so they're not scientific. Sometimes they are, but it's mainly like, here's the author's personal thoughts on this topic. And in my PhD thesis, there is a footnote where I mentioned Vera Rubin, and the footnote is basically me complaining that she didn't get the Nobel Prize, even though she should have done, in my honest opinion. And there's a whole rant about this in a footnote in my PhD thesis. And then that footnote has another footnote along the lines of, one has to wonder if she might have got a PhD, if she might have got a Nobel Prize had she not been a woman. So anyway, if you want the snarky notes and the kind of snarky comments that also show my state of mind while writing my thesis, my PhD thesis is a public document. Feel free to go check it out. It is accessible from my webpage. And, you know, from wherever else you might find me online. It's not on my social media, obviously, but if you want to check out my snarky footnotes and my rant about Vera Rubin, it's there. But we will do this next week. Next week, Vera Rubin Observatory, including a rant about Nobel Prizes. And let's talk about Vera Rubin herself and the observatory, because they're very cool things to talk about. They could call it the Very Rapid Observatory if they want to keep the same initials. Yeah. Would not surprise me if people colloquially refer to it as a very rapid observatory. The very quick, very bright, very big observatory. Stuff like that, yes. We do like doing things like that in science. Okay, back to the top. Where were we? Wait, no, before I go back to the top, there was the question that I wanted to answer about the Atacama Cosmology Telescope. Where was that? It was a question from John. See, I have tried many different forms or many different formats on my science outreach. And one of the reasons why I love these streams is because it allows me to jump from topic to topic. And I feel like this is kind of perfect for my slightly neurospicy brain. Because as you all see, I'm like, oh, squirrel. Oh, someone mentioned the CMB, someone mentioned this. And I get to jump from topic to topic, which is exactly perfect for the way my brain works. But I do know that it means my streams are sometimes a bit chaotic. There is a loose thread somewhere. We just sometimes add more threads and tangents and digressions, but there is a loose thread tying everything together. Question from John. Has the Atacama Cosmology Telescope had some new dark energy results? Not to my knowledge, but so the Atacama Cosmology Telescope, Atacama Cosmology Telescope is a telescope in the Atacama Desert that is measuring the CMB, the cosmic microwave background radiation. This thing here, in case you've forgotten what the CMB looks like in the last 5 minutes since I last put it up. You know, by having this in the background, I permanently have a CMB visible. Do not fall. Of course, it's going to fall as soon as I say it's permanently visible. So it jumped out. Yes. Atacama Cosmology Telescope is a CMB experiment, so it's measuring that. Now, WMAP Planck have gone to space to take the all-sky survey of the CMB. Now, a ground-based CMB mission, instead of taking the full survey, can stare very intently at a smaller patch of the sky. So it gets more resolution, but it loses the overall picture. So it's basically staring very intently at a small patch of the CMB, which allows us to look at the smaller, finer details of the CMB, but we lose the overall picture. So ideally, you want a ground-based and a space-based mission to work together so that we have a consistent picture of the CMB. So the Atacama Cosmology Telescope, per se, is not measuring dark matter or dark energy. It's measuring the cosmic microwave background radiation, and then you can test different models of dark matter and of dark energy using the CMB data. Now, there is the thing that when the first Atacama Cosmology, or when we got data release 4 for the Atacama Cosmology Telescope, there was a slight 2 sigma shift away from our standard model of cosmology, away from the Planck results. Now, when you shift things by about, it was basically saying that it was 2 sigma, the model it was finding was not exactly the same one that we were finding with Planck. Now, this was super interesting and super relevant because that allowed for a lot of models with non-standard dark matter and dark energy to potentially fit the data better, or the Atacama Cosmology Telescope data better. So there have been a bunch of papers over the last 3 or 4 years along the lines of, if we use Atacama Cosmology Telescope data, this dark matter model, this dark energy model is better according to the data than our standard lambda CDM cosmology, which has dark matter and dark energy. However, recently, in spring this year, we had data release 6 of the Atacama Cosmology Telescope, which actually found consistency and alignment with the Planck results. So it seems like there was a slight shift in data release 4, and in data release 6, we've gone back to the expected results. So this means that, once again, our standard model of cosmology is showing to be the best fit to the data. So while it might have seemed over the last few years that Atacama Cosmology Telescope was pulling us away from our standard model of cosmology, the latest data release is putting us back in line with the standard model of cosmology. So the question of, has Atacama Cosmology Telescope shown us anything about dark matter or dark energy? Yes and no. It hasn't shown us anything new, but the newest results from Atacama Cosmology Telescope show us that dark matter and dark energy seem to be behaving the way we'd expect within the standard model of cosmology. So if you liked the new physics interpretation, this was bad. If you like your data to be consistent, this was good. And this is something I discussed in depth in the stream that I did back in spring with the title of New Results in Cosmology. Okay, I'm going to go back to the top and go through the other questions or comments I might have missed. We're going to do some quick fire questions here. Okay, so we talked about the heat wave in depth. Where were we? Let's see. We talked about the question. We talked about dizzy. We talked about the other question that was, where were we? Yes, new results here. There's a quick comment from Ben. Why aren't news agencies mentioning that the resonance frequency of CO2 and methane is infrared? Seems like proof that greenhouse gas relationship is indisputable. I think because that's the type of information that is easy to get lost in the media. It's technical, and it's not catchy, it's not clickbaity, so it's the type of thing that gets lost sometimes. Okay, there's a question from John. I've heard recently about new evidence for direct collapsed black holes. Have you heard of this? I have not. I will have to look into that. I now that you mention it, I seem to remember seeing some news article about it, but not to the level where I could give an answer to that question. So I'll have to look into black hole collapse, because I feel like that's something that I have read about, but I'm missing the details right now. It's not in my brain. Okay. Yes, we talked about the CMB beach ball. We talked a lot about CMB. I'm just catching up with questions. If there's any question that I haven't answered by the time I catch up, please ask it again. I'm not deliberately ignoring questions. There's just sometimes a lot of them, and I lose the thread sometimes. Another question from John. What do you think about the little red dots in JWST images? Is there much evidence for what these are? I'm not sure yet. I know there's been some debate as to whether these are really old galaxies, potentially older than we expect, or really old stars, potentially older than we expect. But it's not something I've looked into enough to have a convincing answer for. Okay. We talked about dizzy. There was a comment from Scott that you were talking with a friend. He said that dark matter and dark energy is just made up to fix the math. How do you counter that argument? Well, It's not made up to fix the math. It's the best explanation we have. The thing is, if somebody is coming from that perspective, it's going to be quite hard to change their mind. But it's not, dark energy and dark matter are not made up to make the math work. They're the best explanation we have for the data. It's not about making the math work, it's about making sense of the data. Our equations don't matter, the data does. And when we look at the data points to the fact that there's dark matter and dark energy. We cannot explain that. We have not found a way to explain that data without dark matter and dark energy. So it's not the math we're trying to fix, it's the data we're trying to explain. The math, you can change your math as much as you want. Every new cosmology model is a different form of math. We're not trying to make this model work. This is the only model we have found that does work given the data. So it's not that we're trying to change the math. The math is what it is. The data is what it is. We're trying to make these two play well together. And the only way we've been able to figure out which model, which math can describe this data, it's the math that includes dark matter and dark energy. So we're not just adding it there because we like our equations to be pretty. We're adding it there because without that, the data doesn't make sense. So it's not just made up to fix the math. It's made up to explain the data, which is basically all of science, right? We make shit up until the data makes sense. And once we find something that makes sense, we stick with it until there's new data, and then we need something new. So yes. Okay, let's see. More questions, more comments. I think we got through all of those on Redshift. And then we got through all of those about Dizzy and Vera Rubin, just catching up very quickly. Okay, I think we got through most of the questions there. Okay, back to the bottom of the questions. So, recap, we've talked about Dizzy. It's a great experiment. There were some new results early in the year, which I talked about in a stream. We talked briefly about Atacama Cosmology Telescope. There were some new results, which I talked about in a spring stream. Vera Rubin Observatory, upcoming experiment that's going to take a huge amount of data. Very, very cool. Okay, so I'm going to do a shorter stream today. I'm almost at the 1 hour mark. I know I've recently got everyone used to doing 90 minutes. I am going to wrap it up now, getting close to 1 hour, mainly because I'm feeling that it is still very hot here, and I'm starting to feel like I'm getting tired, and I'm going to decide that that's a good reason to stop the stream, because I can feel my body saying like, I don't want to chat for another half an hour now. So we're going to cap it at 1 hour stream today, which is a good way to ease back in after not doing it for 6 weeks. I actually have two upcoming streams to announce. I guess it was going to be 1, now it's 2, as soon as my calendar loads. Okay, the plan for the next week, unless there are any unexpected developments, the plan for the next weeks. 1 week from now, which it would be August the 10th, we are going to do a stream entirely about Vera Rubin and the Vera Rubin Observatory. That will be next week. 2 weeks from now, on August the 17th, we're going to do a special stream, because in 2 weeks, actually in 11 days, we are going to mark 10 years since my first live stream. My first live stream, which was on Periscope before then moving to Haps and then settling on YouTube. My first stream, before it was called Cup of Cosmology, my very first stream was the 15th of August, 2015. So we're coming up to 10 years of this. We are coming up to 10 years of me chatting to my camera and hoping people will listen, and you're listening and asking questions. I can't believe it's been 10 years. Cup of Cosmology has outlived several relationships. Cup of Cosmology, or these streams, have seen me through my master's, my PhD, my first postdoc, my second postdoc. It's been a while. It's been a while. So we're going to do a special stream to celebrate. Now, the cool thing is, all of my streams pre-2020, I believe, are not online, because Periscope closed down, so I purged it. They were all purged from online. Some of them are still somewhere on Twitter, but when Twitter got bought over by X, I deleted them, which means you will only have access to my streams from the YouTube days onwards, which is 2022 onwards, with a couple that I uploaded from 2020, 21. So my first streams, the first 5 years of Cup of Cosmology, is not available anywhere, except I have it on a hard drive because I downloaded a copy of almost every stream I've ever done. Which means when we do the 10-year anniversary special in 2 weeks, there will be some clips from my older streams, particularly 2 or 3 standouts. The first one, I actually don't have the recording of the very first stream, but I have a recording of my second stream ever. There's going to be a clip from that. There's going to be a clip from my favorite stream in February 2016. If you all might remember what that date is significant for, you'll see in 2 weeks. But yeah, we will do some kind of recap of 10 years of Cup of Cosmology. So yes, the question about CMB and dinosaurs is one that I'll pin for next week, because I would have to recalculate it, because I honestly cannot remember when we had different CMB wavelengths. So I'm going to shelve that for next week. Yeah, question from David Howden. Did you think it would last 10 years when you started? Absolutely not. Absolutely not. I didn't expect y'all to still be here after 10 years. Some of you have been here since the early days. So yeah, that is that digression, that kind of nostalgia and thoughts, and how cosmology has evolved, how it's evolved with me. You know, all through the TTK years, I have clips from those as well. Yeah, it's basically going to be a trip down memory lane stream. So on the 10th, a week from now, we do the Vera Rubin special. On the 17th, we do the Cup of Cosmology 10-year anniversary. And then on the 24th, I will not be doing a stream because I'm traveling. I will be, where will I even be on the 24th? I'll be on a night train. Yeah, I'll be on a night train. So stream is not happening. I have to upload the archive to YouTube. I'm considering it. Now, the problem is, back in the days, there was no processing. It was just me on a tablet talking and doing things in a very potentially unpolished way, even more than now. Wondering if you are in some of those saved Periscope episodes. You mean in the comments? That's also the thing. In good, do not jump on that fly from the top of your cat. He's chasing a fly. Yes. There's also the thing that all of the old streams, there are no comments saved. The questions are not saved. So it would just be like, here's me talking in front of a camera. I might upload some of them. I would need to do some processing on them, so that's why I haven't done it. But yeah, I have a backlog of about 150 streams on my hard drive that are not anywhere online. And I might change that at some point. I should change it at some point. No, February 2016 was not my doctorate. That was September 2019. But there was a big cosmology thing that happened in February 2016, 11th of February 2016 to be precise. First time that instead of doing an actual setup stream, I just took out my phone in front of the university building to announce something. There will be clips from that. When is the actual 10-year anniversary, though? Either the 14th or the 15th. To be honest, I can never remember if it's the 14th or the 15th. I'm pretty sure it's the 14th of August 2015 was the first one. Yes, the 14th of August. Now, the 14th of August is, I believe, a Thursday, so we will be doing the anniversary stream on the following Sunday, which is the 17th. 3 days late, but close enough. Yes, indeed. As Ange's saying here, February 2016 is the gravitational wave one. And I have that clip where I announced, or where I talked about the fact that they just announced the first discovery of gravitational waves. That one will feature in it, yeah. So I need to kind of pull these clips up because for now they're just on a hard drive, but they exist. And before the 17th, I will get them all ready. There might also be some of my all-time favorite clips appearing, because of course we have to do that. Okay, so yes, the first LIGO detection, indeed. I have the stream I did. Like, they announced the LIGO thing. I watched the live stream at work with colleagues, and after about 10 minutes, I left and did a live stream so that you all got my reaction, my live reaction, basically, to the gravitational waves, my first impressions, my first thoughts. And it's a very fun stream. So, as I said, 10th, next week, there will be a stream about Vera Rubin and the observatory named after her. On the 17th, we will do the Cup of Cosmology 10-year anniversary, and that's going to be fun. Feel free to bring cake. You know, I cannot provide cake for you all, but feel free to bring cake. Yes, Ben, you just confused me there where you said you were in some of the episodes, because like there was someone called Ben on the episodes, but that was not you, right? Yes, okay. Yeah, the problem is the comments are not safe, so I don't know who was saying what, but I just have me talking to a camera. We'll see what I do with those clips someday. Someday they might appear somewhere. We shall see. But yes, of course, all of these future plans have the caveat that if for whatever reason my health takes a bad turn, because as some of you know, I am chronically ill, these streams always have the caveat of health permitting, if I can. But the plan is on the 10th, we talk about Vera Rubin. On the 17th, we do the anniversary special, a cup of cosmology, 10 years in the making. And that's going to be a fun one. And then there will be a week gap. And then in September, new schedule, potential guests. I haven't had guests in a while because things have been chaotic, but stuff is happening. Point being, Cup of Cosmology is back. I know I've been gone for 7 weeks. Cup of Cosmology is back. There are plans, there is stuff happening. I'm so happy to have you all here. I have new props. Great to have regulars and new people coming in, as always. So, thank you everyone for joining today. This has been super, super fun. Thank you to have everyone here. Thank you to everyone for being here. It's great to have everyone here. That was the 2 sentences I just mumbled together. We've had some very fun questions, some very fun comments, as always. It is really, really nice to see you all here, to have you all here asking questions. Cup of Cosmology should be back online Sunday next week, same time as always. There is a schedule on cupofcosmology.com. There's a time zone converter where you can figure out when I'm going to be live, but same time as always, 1 week from now. I hope to see you all then, 1 week from now, for a Vera Rubin special. Thank you everyone for joining. This has been great fun. See you next Sunday. And I hope in the meantime, you will take care of each other and stay curious.